So in the previous session, we have learned about the Boolean function and the function of Boolean expressions. So with this knowledge, I'm going to explain what is there in my in the note which I'm preparing. Definition 6 is very important. Just carefully observe that a Boolean expression of this form is said to be a min term. It's a word, and do not ask me why this word is min term. Okay, and there is corresponding to that there is one dual term is there which is called max term, which we'll later see. It's said to be min term in the variables x1, x2, xn if it is of the form x1 bar into x2 bar into xn bar, where each of these xi bars can take two values. One is xi or xi complement. Okay, so this is called min term. This is the definition of min term. With the definition of min term, one important property of Boolean algebra can be defined. What is that property? The property is written in the definition 7. It is saying that a Boolean expression is there, alpha x1, x2, xn. This Boolean expression is said to be a disjunctive normal form or DNF or sum of product form. Okay. In the variables x1, x2, xn, if there are min terms, of the form alpha 1, alpha 2, alpha m. See, I have used here the subscript m, and it is different from n. Here, this alpha 1, alpha 2, alpha m, these are the some parts of x1, x2, xn in the variables x1, x2, xn, such that alpha can be expressed as the sum of these min terms. By looking at the definition, it is not clear at all what is this going to say until and unless we try to deduce it from a problem. This definition, once again, we can go through, but later, after explaining the problem which is following right here at this moment. Once we discuss the problem, then again we can come back to the definition to understand whether the problem that I'm going to do is telling with the statement made in the definition or not. Okay, but we have not understood a single thing about these min terms and this DNF form. Okay, let us consider a Boolean expression alpha equal to x1 complement plus x2 cross x3. We can consider this type of Boolean expression, no problem. Why can I consider this type of Boolean expression? It is because you see that alpha, when it has this type of expression, is nothing but a kind of expression containing the inputs x1, x2, x3, which is x1 complement plus x2 dot x3. So you can say that alpha is a function of x1, x2, x3. So obviously it is a Boolean expression. Now we are going to prepare a chart, and you know that each of these xi's can take either value 0 or value 1 by the property, by the rule. So we are going to prepare a chart over here. In this chart, what we have done, we have counted all the possibilities, all the possible values that x1, x2, x3 can take, and we have tabulated them. Some values have been colored. Why they are colored, we'll come to that point later on. But we have prepared the chart and we have tabulated all the values. Corresponding to the Boolean expression given, first of all, we need to calculate x1 complement, and then we need to calculate the product of x2 and x3. And we know that 1 complement is 0 and 0 complement is 1. So under the column x1 complement, we have introduced zeros and ones accordingly. x2 and x3 have been multiplied with one another with the multiplication rule on the 2-element Boolean algebra. I'm not going to explain that rule in detail. It has already been explained. So here are the values that you have in front of you. And then once we get this fourth and fifth column, the fourth and fifth column are added with the addition operation defined on the two-element Boolean algebra. Then my table is complete. Once my table is complete, you see that I have highlighted only those expressions which are having output 1 and have not highlighted the expressions which are having output 0. You can relate the situation with the switching circuit case where 1 corresponds to that current is flowing from one end to the other when the switches are closed, and 0 corresponds to when the current is not flowing from one end to the other when the switches are open or the circuits are open. Once we highlight this one output or flowing of current, we are highlighting them and we are trying to mark for which possible triplets of the Boolean variable this is happening. And we have come to see that in the row 1, that means this row, output is 1 when we place 1, 1, 1 for the variable x1, x2, x3. Similarly, this non-zero output is happening and occurring for row 5, row 6, row 7, and row 8. I have written this over here. Do not think that I am multiplying the thing. Probably my writing is not that good. It is, what I mean to say over here is that the image of 1, 1, 1 under the expression alpha is 1. In the row 1, it is appearing. Later, I will try to format the thing for more clarity. Now, corresponding to row 1, what we can analyze? We are analyzing that corresponding to row 1, we can redevise one Boolean expression of the form x1, x2, x3 can be written as x1, x2, x3, their product. Why? Because we are defining it. Why? Because you see, if I define alpha 1, this alpha is not, it's not alpha, it is alpha 1. It only corresponds to row 1. If I write the expression as x1, x2, x3, and if I put 1, 1, 1, you see that 1 into 1 into 1 will give you 1. And for this formula, no other case is there. Other cases, b1, b2, b3, any other triplet, b1, b2, b3, corresponding to alpha 1, which is where b1, b2, b3 is not 1, 1, 1, will give you the result, the output is 0. Second, you come to row 5. Okay, let us see the row 5. You just look at the chart. This is your row 5. Now, in row 5, you can, what are the values? We have 0, 1, 1. So what we can do, you can put x2 to be 1 and x1 to be 1. Their product will be 1 into 1 will be 1. But you cannot put x1 to be 0. Otherwise, the product with the output will be 0. So what you can do, in place of x1, you can put x1 complement multiplied by x2 and x3. x2 and x3 remaining same. We are writing here x1 complement. And if I write this, if I call this Boolean expression as alpha 2, and if I substitute in place of x1, if I substitute 0, then 0 complement will become 1, x2 is 1, x3 is 1. So 1 into 1 into 1 again gives you the output, which is coming in the row 5. Any other input, any other triplet, which is not equal to 0, 1, 1, corresponding to the Boolean expression alpha 2, will not yield in the output 1. And similarly, you can redesign your outputs by considering different 3 other Boolean expressions of the form alpha 3, alpha 4, alpha 5, where you will see that if I substitute the values of x1, x2, x3 as 1, 1, 1, or 0, 0, or like that, if I put here x1 equal to 0 and x3 equal to 0, so we will get 0, 1, 0. For this, I'm writing here for your clarity. So I have considered, just a minute. If I take x1 equal to 0, x2 equal to 1, and x3 equal to 0, so what you will get for 0 complement, you are going to get 0, sorry, for 1 you are going to get 1, and for 0 we are going to get 0 complement, that is 1. So output is 1, and it is happening for alpha 3 0 1 0, which corresponds to row 6. Here we are going to consider x1 equal to 0 and x2 equal to 0 and x3 equal to 1. You will get this. Here we are going to consider x1 equal to 0, x2 equal to 0, and x3 equal to 0. You are going to get this. In this manner, we can, for all the non-zero outputs, the rows can be associated with the Boolean expression. Now the Boolean expressions that I have designed, now how many rows were there? Okay, how many rows were there? Just let us write it over here. We had row 1, we had row 2, we had row 3, we had row 4, we had row 5, we had row 6, row 7, row 8 in the chart. And corresponding to each of these rows, x1, x2, x3, these three variables were involved. This row, row 1, row 5, row 6, row 7, row 8, for these rows, you have defined Boolean expressions like alpha 1, alpha 2, alpha 3, alpha 4, and alpha 5. Alpha 1 was a function of x1, x2, x3. Alpha 2 was a function of x1, x2, x3, and so on. This alpha 1, alpha 2, alpha 3, alpha 4, alpha 5, these are called the mean terms. Mean terms in variables x1, x2, x3. So our mean terms are alpha 1, alpha 2, alpha 3, alpha 4, alpha 5. If the definition of mean term is not clear from the definition itself, it is now clear from the example. We are considering the sum of these mean terms. We are considering now the sum of these mean terms. Okay, alpha 1 plus alpha 2 plus alpha 3 plus alpha 4 plus alpha 5. Where we are considering the sum of the mean terms, let us try to go back to the definition where it is written. Okay, so let us scroll up a bit. Just see. Once we get the mean terms, alpha 1, alpha 2, alpha m, m is different from n, then we have to consider their sum. Alpha 1 plus alpha 2, alpha m will be denoted by alpha, and that is the requirement for disjunctive normal form. Okay, so therefore, after getting all our mean terms from the example, we have taken the sum of these mean terms and we have denoted this sum by alpha beta. This Boolean expression beta is actually called the disjunctive normal form. Now we had initially alpha. Initially we had alpha. Alpha was given by this expression, as you can see. This was the expression of alpha, and several alphas have been designed, and their sum total is giving you another Boolean expression. Let us try to find out whether these two Boolean expressions, alpha, original one, and beta, which is the sum, which is the disjunctive normal form, whether they're Boolean, these two expressions are same or not. So I have done a little bit of calculation over here, okay, in details that you can very well reproduce by yourself. So I have written all the possibilities of x1, x2, x3. Alphas have been calculated, and alpha 1, alpha 2, alpha 3, for all these possibilities have been calculated by looking at the form of the function. And then beta means their addition has been taken into consideration. What we have found is that alpha and beta, they are having the same values altogether, and which means that they are Boolean, these Boolean expressions alpha and beta, they are same. So from the above table, it follows that Alpha and beta are same, and so alpha is also in the disjunctive normal form. So alpha, this Boolean expression, what we have found actually is that this alpha, the original Boolean expression, can be expressed in terms of disjunctive normal form. So I have considered a example which is quite large enough. If you are sitting for online examination, then very simple facts from these DNFs and related things can be asked. If the mathematical subtlety is clear to you, you can answer any question. If it isn't clear, then you will face the trouble. Here in exercise, you are going to find the Boolean expressions for each of these tables. Boolean expression in terms of DNF. So suppose let me do one problem for you, and you will try the rest. So we have this chart. What is the question? Question is that find the Boolean expression in DNF. Find the Boolean expression in DNF for each of the Boolean function given by the following. And we have in problem number 1, we have the chart as it is given. X, Y, Z is having value, possible values 1, 1, 1, and the output is 1. Now what you see is that we can define in this part, for this particular case, we can, this output can occur with respect to this X into Y into Z. This is a simple DNF expression for this output. If I consider the second one, then if I multiply X and Y, you will get 1, no problem. But if I multiply by 0, the output will not be 1, but output needs to be 1. So you can have, for this, we can have X into Y into Z complement. For the second one, third one, we have X into Y complement into Z. For this one, we have X into Y complement into Z complement. 0, 0 output will not be taken into consideration. One output, this one can be considered as X complement, Y complement into Z. All these are associated with, so these, what are these? This is your alpha 1, say, this is your alpha 2, this is your alpha 3, this is your alpha 4, and this is your alpha 5. And these outputs have been obtained somehow, which corresponds to alpha. Now the question is, you are going to express this alpha in terms of these mean terms. So all these alphas are called what? These are mean terms. So we can express this alpha by the product of by the sum of these mean terms, alpha 4, alpha 5, and so on. And if I, or you can write xyz plus xyz prime plus xy prime z, sorry, dot, plus xy prime z plus x prime y prime z. And you can easily show that alpha and beta, these two expressions are actually same. They are they are same Boolean expressions. So indeed, this in the problem, in this particular problem, the function has been expressed in terms of mean terms, or it can be expressed in terms of DNF. Okay, so it's a very simple example, and you can similarly you can find the DNF form of the second one also. And corresponding to, now let us go back to the definition of DNF. Okay, once more. So what was the definition of DNF? The definition of DNF went like this. So we had Boolean expression alpha x1, x2, xn. It is in disjunctive normal form in the variables x1, x2, xn if there are mean terms in the variables x1, x2, xn, so that alpha can be expressed as alpha plus alpha 2 plus plus alpha n. Now, if I define in a similar manner, if I define a quantity or entity called max term somehow, in the definition of min term, you have used the symbol xi bar, and for all xi bars have been taken, their product has been taken. So we had x1 bar into x2 bar into xn bar like this. You called it min term, isn't it? Now, if you want to define something else, if I define something like max term, replacing all the product by plus, and in the subsequent definition, if I consider all these max terms and express a quantity called alpha by the product of these max terms. So here I'm replacing the product by sum, calling them max term, and here I'm replacing sum by product. Then this type of expression is called conjunctive normal form, or CNF, which has been written in the following definition. So just look at the definition. I'm not going to explain the problem. We have already understood. Just go through the problem of DNF once again. You can find by yourself. So a Boolean expression C has been defined in the following manner. All the products have been replaced by plus, and here in the subsequent definition, the expression alpha has been replaced by the product of different max terms that have been found. If this can be done, this type of alpha is actually called is said to be in its conjunctive normal form. And here I have given once again 2 tables for you, and in these 2 tables you are going to find the conjunctive normal form of the following. Now, it's not quite difficult. You don't have to write so many things if you have understood the matter correctly. Let me do this particular problem for you. First of all, what you need to do, you are going to mark the output, which is 1. Here also. Somehow you have obtained alpha. Now, corresponding to this output, just think of the table that you had in your mind, the plus table for 2-element set. 1 plus 1 was 1. So what we can do here is that no, just a minute. Here we are not going to mark this, because since from duality principle, everything is being replaced by its opposite. Plus is being replaced by dot is being replaced by plus, and duality principle also said that you need to replace 0 by 1 and 1 by 0. But in disjunctive normal form, we were interested about 1. Now we will be interested about 0. One will not be considered over here, because we are not defining disjunctive normal form. We are going to define the conjunctive normal form. Once we define this, then corresponding to, and this is your alpha, corresponding to this 1, 1, this output 0, what you can do? You can take the x complement plus y complement plus z complement, because you know this is your alpha 1. Because you know when we add these terms, isn't it? When we add these terms, 1 complement is 0, so 0 plus 0 plus 0 gives you 0. Here 0 plus 0 is 0, but here 1 is present. It shouldn't be. So for this, you need to write it as x complement plus y plus z. That is your alpha 2. Here you need to write it as x plus y complement plus z. This is your alpha 3. And here you call it x plus y plus z complement. That is your alpha 4. No other outputs will be considered because other outputs are non-zero outputs. In the disjunctive normal form, we consider the output 1 and we expressed the min terms by the products. Here we are considering the output 0 and we are defining the max terms by sums. All these are max terms, remember. Once we get all these max terms, your conjunctive normal form will be, that means your alpha will be expressed as the conjunctive normal form, as it can be expressed as the product of these max terms. So you can write it as this into this into this into this, which is alpha 1, alpha 2, alpha 3, alpha 4. This is called the conjunctive normal form, in which the Boolean expression has been devised. Okay, so this is the last topic of your Boolean algebra section of your syllabus. Okay, and very briefly they have gone through this topic. No further detailing is there, so I'm not going to get into the further details of on this Boolean algebra. Boolean algebra is a big topic where lots of other things are there, but I'm intentionally skipping all of this. With this, I'm going to conclude my unit 4. From next week onwards, I'm going to quickly go through the sections of graph theory, and I had already shared a book with you. First 3 chapters of a book. So you just quickly go through those chapters, and so that I can quickly explain the relevant parts of that section. Okay, we do not have much time. The examination is knocking at the door. So with this, I'm going to end my today's session. If you want to write your roll numbers in the chat box, you can write, or if you can skip, because I have already saved the previous chat. So your attendance is there with the previous chat. You don't have to write anything over here. Okay, so I'm going to conclude my today's session. See you in the next week.